Oh,
Yeah, just a second. I'm just waiting here.
okay.
Okay. Hello, everybody. Welcome to the closing lecture of this compact and virtual edition of the Ciclo de Cursos Especiais. It's a pleasure to introduce our invited speaker today, Dr. Ewine van Dishoeck. I hope I spelled your name correctly. Dr. Ewine is professor of molecular astrophysics at Leiden University in the Netherlands, an external scientific member of the Max Planck Institute for Extraterrestrial Physics in Garching. She graduated at Leiden University and held positions at Harvard, Princeton, and Caltech from 1984 to 1990, before returning to Leiden as associate professor in 1990. She became full professor in 1995. Van Dishoeck has guided and mentored dozens of students and postdocs. The research of her group uses ground and space-based observatories together with laboratory experiments and modeling to study the molecular trail from star-forming interstellar clouds to planet-forming disks. Van Dishoeck has been heavily involved in planning new observational facilities such as Herschel, ALMA, and JWST, and holds many national and international science policy functions, including President of the International Astronomical Union, Scientific Director of the Netherlands Research School for Astronomy, NOVA, co-PI of the JWST MIRI instrument, and former ALMA board member. She has been fortunate to receive many awards for her multidisciplinary research, including the Dutch Spinoza Award and the Dutch Academy Prize, the 2015 Albert Einstein World Award of Science, 2018 Watson Medal of the US National Academy of Science, and the 2018 Kavli Prize for Astrophysics. So, Dr. Ewine, it's a pleasure to have you here. I hope we have the chance to have you back in Brazil personally when all this is over. And please go ahead.
All right. Good afternoon, everybody. It's really my pleasure to be with you virtually and take you actually on a tour of interstellar space and see how we can make new stars and new planets there, and also how we can build sort of the chemistry that ultimately is the building blocks of life in those regions. So, but first, let me say that we are far away. I'm far away from you, but yet, thanks to all of these, Zoom meetings and everything, we are more connected than ever. I've been virtually in India, in the Middle East, in South Africa, and now in Brazil, just in a time span of 2 weeks. And of course, I wouldn't have been able to do that if we really had to travel there in person. So well, yes, it's a great loss not to be able to look each other into the eyes. At least we can communicate still, and we can still ponder sort of our beautiful sky and our own little Earth here, as you see over here. So I'm going to tell you a little bit about the story of molecules from clouds to disks and planets. It's in a number of subtopics, a little bit about background. Not all of you may be familiar with interstellar space, and not all of you may be familiar with chemistry. And so it's a little bit here in a play and a plot, as you can see. I will stop for a couple of minutes after each topic to give you an opportunity to ask questions. It's better if we do this already along the way, then we do everything at the end. So that also makes it a little bit more lively. So be prepared already to ask questions in between rather than save them all for the end. All right, good. So the big questions. Undoubtedly, one of the most exciting developments in astronomy has been the discovery of planets around other stars, the exoplanets. Of course, Nobel Prize awarded to them in 2019. But also we are learning so much about them almost on a daily basis. We now know that they are very abundant thanks to the Kepler satellite and the radio velocity studies. On average, every star has maybe of order 1 planet, but many of them are of a kind that we don't have in our own solar system, the super Earth and the mini Neptune, so a few times the mass of the Earth, Neptune of course being about 10 times the mass of the Earth. So why is that? What sets that actually? And also, what are their building blocks? And this is, of course, touches on my own research here. And the astrochemistry part is really what are the chemical building blocks that we have available for making these planets. And directly related to that is also the question as to how we were actually formed some 4.5 billion years ago. And we still have messengers from that early solar system time. We have, of course, the comets. Comets consist of rock and ice, and they are probably the best preserved in the outer parts of our solar system for 4.5 billion years. And excitingly, we have gone to a comet and landed on it with the Rosetta mission and scooped and sniffed sort of the material that came out of the comets. And I'll say a little bit about that at the end. The inner solar system, also exciting new results. You've probably heard all the excitement about OSIRIS-REx actually landing on Bennu and scooping up some material and returning it to Earth for examination in laboratories on Earth. The same, the Japanese mission Hayabusa 2 going to Ryugu. It's already on its way, and I think next month it will actually land in Australia, and so then we can start to really examine in laboratories on Earth this very primitive material. So that will be a very exciting time. Okay, that's sort of the big questions. Then sort of where do we find molecules and how do we actually build them? Are you all familiar with these beautiful images of the nebula? Here the Orion Nebula with the Hubble Space Telescope. You all probably know that what you're looking at here in the colored emission, that's the ionized gas, that's the H alpha and other ionized lines. This is gas of 10,000 degrees, and there is not much chemistry, molecules going on there. And we really have to go to the dark part that you see over there. And that is where we will find the molecules. And we probably see that best here in this, again, HST, the Carina Nebula on the southern sky, where you see sort of these dark clouds against the bright nebular background. Now, these are some of the largest objects that we have in our galaxy, also the most massive. They contain enough mass to make maybe 100,000 new stars, 10,000 new stars. They won't do that. They will do it only with an efficiency of only 10%, a few percent actually, which is a whole story in itself. I could give a whole lecture about that, but that's not today. But they are the reservoir out of which the future stars and planets are actually being made. Typical conditions are that they are cold, only 10 to 20 Kelvin, and densities typically 10 to the 4 to 10 to the 5 per cubic centimeter. And of course, they are so dark because they contain these tiny dust particles, about a tenth of a micrometer in size, that actually absorb and scatter the light. Okay, so the big picture here of star and planet formation is that we start out with one of these diffuse, fairly dense clouds already. We actually have already some molecules there, carbon monoxide, triatomic molecule here, H3+, important for kickstarting chemistry. But also some of the more larger molecules, the polycyclic aromatic hydrocarbons, very sturdy molecules. They can survive sort of the UV radiation. And that's why they are also present in these diffuse clouds. But it's really, if you go to these denser shielded regions from the UV radiation, that the chemical complexity starts to grow. And these are just some of the molecules that we find there. Water, I'll talk quite a bit about water. Also, say, formaldehyde, dimethyl ether, which you see over here. And then these mysterious, very long carbon chains. Mostly carbon and just one hydrogen, in spite of the fact that there's, of course, much more hydrogen than there is carbon. So that gives already an indication that the chemistry in space is not in thermodynamic equilibrium, that we really have to look at the kinetics that are going on. You go to accretion disks, the disks around the young stars. Of course, the cloud always has a little bit of rotation, and when it collapses, it forms not just a star, but a part of the material comes in a rotating disk around a young star, and that is where we are now also with ALMA starting to probe the chemistry. You form planets there, you form maybe planetesimals there, comets. And again, those are very rich in chemistry, and they can actually land on a young planet there. And then finally, at the end of the life of a star, it swells up. It then creates conditions in which you can actually make lots of molecules again. Here in the mass loss state, you have very dense conditions and warm. You start to condense out minerals, but you also make molecules like these buckyballs that you see over here. That material, of course, goes back into the interstellar medium, and then it has again the cycle. So what we see here already is that we find specific molecules under specific conditions, and this means that we're not just studying chemistry, but we also use these molecules as a probe of the physics that is going on. They tell us about temperatures, they tell us about densities, and they, of course, are the way to probe kinematics, dynamics, etc., through their line profiles. It's actually a very interdisciplinary approach. We have the observations that I'll come to in a minute. We have models, of course, of the chemistry and the physics that is going on. And then there's the laboratory, basically, that is underpinning all of this, both observations and models. And this laboratory, that can also mean quantum chemistry calculations of, for example, collision rates that we need to know in order to interpret our data. And I know that also in Brazil, there's quite a bit going on in terms of astrochemistry, astrobiology, for example, with the synchrotron light sources here, the one near Sao Paulo, and the Sirius. Some experiments are being done there, but it's really a wonderful time in which sort of chemical physics experiments, and astronomy are actually coming together to simulate the conditions that we have in interstellar space. And then also, say, the mass spectrometry, like you have here, that you can actually investigate particles like those that are being brought back from the asteroids, that you can actually investigate those in detail. Okay, so let me stop here and see if there are already any questions.
Any questions?
You have to. I cannot see the questions, so one of you has to has to ask me the questions. Yeah. Okay. If there.
Yes, there is one question here. Go ahead, Daniela.
You were speaking about in the dense clouds that you have these long chains of carbon. They have been seen in another places. I am not really a chemist, but
well,
they exist somewhere else.
Yeah, you don't find them easily in a laboratory on Earth. You do find them, they are really very specific to interstellar chemistry. It's very interesting, actually. That's very, very curious molecules. They're not easy to make on Earth. They are stable molecules, but they're just not easy to produce.
It's not interesting.
I have a question, in fact.
Yeah.
So we know that there is a radial gradient of abundance in the galactic disk. So is there any correlation observed with molecules, a gradient of molecules in the disk also? And what's the range, what's the most distant cloud that we can have been already observed?
Yeah, so two very good points. I think the most distant clouds is really at the edge of the universe, and we have seen molecules already in galaxies at redshift of 7 or 8. So carbon monoxide, water, ionized water. So these molecules are there already in the high redshift universe. In terms of gradients, we see them in the isotopologues. So 13C over 12C or 18O over 16O. Those are the kind of gradients that are reflected in the abundances. Not so much in terms of overall chemistry. That would only come in when we start to get to, say, small Magellanic Cloud conditions, where you also have less dust, of course. I mean, as we will see in a moment, we'll need dust actually in order to make the molecules. Yeah.
Okay, thank you.
Okay, good. So let's actually continue. How do we observe this? So optical pictures are nice, but that's of course not when we can penetrate into the clouds. For that we need actually infrared observations. And wow, here we see actually from Spitzer, these are actual Spitzer data, where we go from basically, this is an optical image, and we basically shift the wavelengths to infrared. And what we see then, if we go to the infrared, of course, you could look through the dust. And now we also see that inside this cloud, there is a young star that is trying to push away already its surroundings, the protostar. And what you see there is the outflow, the jets and the outflow with which it tries to do that. So that is one thing. And the other thing is that when we have such a protostar, basically, here collapsing inside a cloud, an embedded young star. And then, of course, it heats up the dust around it. So that is actually what you saw in this image at Spitzer at, say, a few microns. That's hot dust at a few hundred to 1,000 Kelvin. But what you can, and that provides here the continuum sort of emission. But then what you can do is actually look along the line of sight, this sort of then functions also as a background lamp that you can actually look along the line of sight and see sort of the absorptions superposed on it. And what do you see in the infrared? In the infrared, you actually see the vibrational transitions of molecules. And you can see them both of gases, like water, but you can see them also of solids. And that's unique to the infrared wavelength range. And the infrared is basically where we can really see the composition of the silicates, where we can see the composition of the ices. So this is the same protostar, but now rather than looking in continuum, we take a spectrum of this source. And what we see here is actually this here, the continuum, and then these deep, very deep absorption features here. You see the flux is dropping by 3 orders of magnitude. Very strong absorptions by water, by carbon monoxide, by the silicates. This is the silicate feature that we see here, but then here in the bottom is ammonia, methanol is here, and carbon dioxide is what you see here. So this tells us already, if we now quantify this, that actually in these dense clouds, a lot of the elements are not in the gas. A lot of them, the heavy elements, are not in the gas, but they are actually locked up in these cold ices. So here you see actually in the bottom of the silicate feature is where you see ammonia and methanol, and these are actually two very important building blocks for making complex organics. So in the infrared, we have fantastic facilities. We, of course, have in space, we had Spitzer, we had the Infrared Space Observatory, we had Spitzer, we had Herschel. Until a few years ago, we now still have Sophia. Of course, on the ground, we have the VLT, which can look at least in a few limited wavelength ranges. And then we are all waiting for JWST. We are a bit exhausted from writing all of our observing proposals, which were due earlier this week. Then there's the extremely large telescopes. Of at least one of them, the ELT is less than 10 years away. So exciting opportunities also in the infrared range. So the other way to detect molecules is not through their vibrational mode, but the molecule can also rotate end over end in space. And that is actually what you are observing in the millimeter wavelengths range. So when a molecule rotates, so this is the rotational quantum numbers, here j equals 0, j equals 1, j equals 2, j equals 3, etc. And what happens basically is that such a molecule can collide with another molecule, be brought into a higher energy level, and then it can decay again, either through emission of a photon, and if that photon escapes from the cloud, it can end up on our telescope, or it can actually be collisionally de-excited. And so this is actually the way, if it emits a photon, and that is actually the main method to detect interstellar molecules. But we can only do it for gases. Of course, a molecule that's in a solid, it can vibrate, but it cannot freely rotate. And so this only is for gases, but the advantage is then it's a huge sensitivity. We can go down to abundances of 10⁻12 with respect to hydrogen. So very great sensitivity. Also, the technology here, the heterodyne receivers naturally have a very high resolving power, orders of magnitude higher than anything you normally have in optical wavelengths. So we can see kinematics down to 0.1 or less kilometers per second. So that is what we get from the line profile, and from the line strengths is basically how we get the abundances. And through the line ratios is basically how we get information on temperatures and on densities. So this is an example of such a spectrum that these days you can get in less than 30 seconds. If you point your telescope at Orion or anywhere else, and you see it's just chock full of lines. And by comparison with catalogs of lines on Earth, you can actually identify all the different molecules. They have their unique spectrum, their unique fingerprint, thanks to laws of quantum mechanics. So for example, here of dimethyl ether, we see here's 3 lines and here another line. And so this is a firm identification of that molecule. Basically the spectroscopy is accurate to 1 part in 10 to the 7. The only thing you need to know is the velocity of your cloud with respect to Earth. But that's always very well known from just the strongest line, carbon monoxide, and then all the other lines basically fall into place. All right, so how does it work? So here we have an example of a Herschel spectrum, and then this is just a tiny little blow up of that spectrum, and then you see already that all of these lines here we can fit sort of as a mix of molecules. Methanol is usually one of them, but also sulfur dioxide and more complex organics. This one is, of course, well known also to everybody. That's actually alcohol. So just to give you an example of some recent new detections, we are already at tricarbons, like here the cyanides, propyl cyanides that are seen here. Now also with some side change, which are sort of characteristic also of amino acids on Earth. I should say no amino acid has yet been detected, but these have been seen. The first chiral molecule has been detected, that is seen here. We cannot yet determine whether there is more of the left-handed or right-handed, but certainly for that you need polarized light. But at least it's interesting that the first chiral molecule is there. And this is also very interesting new detection in cold clouds, actually, where you can see molecular complexity already going all the way to benzonitrile. The astrochemistry machine is clearly ALMA. And fantastic to have seen that come together. A worldwide project in astronomy from North America to East Asia and Europe to put it together here on this high altitude plane in northern Chile. What do we observe as ALMA? So we observe continuum. Continuum is always called to the thermal emission of cold dust. And then the lines, of which there are 10,000s of lines, and that is basically all these molecular lines that you just saw. And it was actually wonderful to see ALMA come together. Think about also the logistics of that for a moment. You have 3 partners across the globe, and all of them need to bring their components to northern Chile and then integrate them into the telescopes, test them at the mid-level facility, and then put them on a big truck and drive them up the mountain to put them into the array at 5,000 meters. So it's truly a breathtaking experience, both literally and figuratively, to be there. You see actually on my background there, that is also the Nicancabur and the ALMA site is just here off to the right. Okay, any further questions here? Any comments?
Yeah, we have some questions. I'll read one question by Jana Martins, who's a PhD student at the Valongo Observatory. How do you see the future of theoretical and experimental astrochemistry with the upcoming data of JWST?
Yeah, well, JWST will be very good at observing ICES. So JWST is very sensitive, much more sensitive by 2 or 3 orders than Spitzer was, for example, or than any ground-based facility. So it will be very powerful for ICES, but it has a resolving power, a spectral resolving power of at most a few thousand. And that means it's not so good at gas phase molecules. It will say a few of the more prominent ones, but I think one of the strengths of JWST for astrochemistry will really be in ICES and ice mapping, rather than just looking for individual lines, a few lines of sight. So, and then again, that will require also laboratory data then to support it.
Okay, thank you. And now Andres has a question too.
Hello, Dr. Ewine. You show a plot with some samples of some molecules detected, and most of them are based on carbon, as expected. But I just wondering, what is the complex molecule in terms of its atomic structure that has been detected in the stellar medium so far?
The largest, sorry, I missed the one word. The
complex molecule.
The most complex.
In terms of its atomic structure.
Yeah, indeed, most of the molecules are organic. I'll come back to that in just a moment as well. Sort of 75% of them, and then they are obviously carbon-based. For a long time, HC11N was the largest one. Then it was that detection was disputed, and then it was rediscovered again. So it's one of these cases that goes back and forth. Of course, the polycyclic aromatic hydrocarbons, there we have not identified in individual molecules. We only know them as a class, except for benzonitrile now. So some of those molecules are now the largest ones. As are C60. I mean, that would be sort of the most complex in that respect. But as we will see in a moment, going much larger, we are starting to reach the confusion limit with ALMA. So let me come back to your question in a second.
Okay. So I have another question by Jana. How can we improve our identification of molecules in the infrared when compared to radio, once you have only signatures of some bands like CC and CH?
So this is a good point. So the rotational spectroscopy is incredibly accurate. So in terms of identification, there we have unique lines, but you're quite right that in the infrared, it's much harder because there we have typically functional groups. So the small molecules are still unique. So CO2 is unique, and we have multiple bands of that. We have the stretching, the bending modes. We have the 13 CO2 features. So a molecule like CO2 is secure. But once we get to more complex molecules there, and think of something like acetaldehyde, CH3CHO, or something like that, then it becomes already difficult to say, is it really this molecule or not? Because it's not as unique spectroscopy as in the millimeter wavelengths. So yeah, that's going to require quite a lot of lab experiments and then searching for multiple bands of the same molecule for identification. I think the ones that I showed, ammonia, CO2, even methanol, those are all secure.
Okay, so no more questions now. Thank you.
All right, let me then continue with a few of the main players. So here are the ingredients. Just to remind you of abundances, of course, it's mostly hydrogen. And sort of the other elements are at a minor level with respect to that. And then, of course, some fraction of these elements, like of silicon, the bulk of that is actually locked up into the grains. And also a fair fraction of carbon is actually in refractory form. So the periodic table of the astronomer looks a little bit different from what you had in your high school chemistry. It's really dominated by hydrogen here. So in terms of the identified gas phase molecules, here's also your question in the HC11N that you have there. There are now more than 200 in total. That's not including the isotopologues. And interestingly, we still increase by about 3 per year. And as you can see, the bulk of them are organic molecules, but also a number of inorganic molecules. So let me say a few words about the chemical processes. I'm going to go through this rather quickly, but I think it's important that you sort of know a little bit about it. So as I said already, the chemistry in space is such that it's not in LTE. It's not thermodynamic equilibrium chemistry. It's really determined by two-body reactions, sort of the kinetics between the various reactions. And there are not that many different ways actually to form a bond. It's actually very difficult to form a bond in space, because when you bring two species together and you make a molecule out of it, that energy of that bond, which is a few electron volts, has to go somewhere. And in space, the only way it can go is through radiation. And radiation is a slow process compared to its collisions. So it's not that easy to make a bond in interstellar space. That's also why, in the gas phase at least, that's why we invoke also these grain surfaces in order to do that. Once you have a bond, then you can destroy it. UV radiation is very effective at destroying molecules. And also this process, recombination with an electron, is also a very fast process. The way we build larger molecules in the gas phase is then through these ion molecule reactions, actually, in order to make them. And UV radiation and cosmic rays are very important in that. So let's just take water. I'm going to now go through a number of examples as to how you actually make water in space. So this is actually the route through low temperatures in diffuse interstellar clouds. It's a series of these ion molecule reactions. You don't have to know the details, but this produces actually, a little bit of water in interstellar clouds. A little bit meaning at the level of, say, 10⁻⁷, 10⁻⁸ with respect to hydrogen. And it's driven here by the cosmic rays, actually, that can penetrate the cloud and create this ion H3+, and that actually triggers a lot of the chemistry. And we know now that this chemistry is working because we have seen a lot of the intermediates. We've now seen actually OH+, H2O+. We've all seen these intermediates now with Herschel. So that is, on the one hand, a confirmation of this chemistry. It also provides us with a diagnostic, because the initial step, it depends on the cosmic rays. So now we can use actually the measured abundances as a probe of the cosmic ray ionization rate, which is important for the physics of star formation. So this is the low temperature route. But there's also a high temperature route, because you may be wondering why not the obvious reaction, oxygen plus molecular hydrogen. We know that the cloud is mostly molecular hydrogen, so why doesn't it react? Well, it doesn't react because it has an energy barrier. So there's an energy barrier of about 2000 Kelvin, which means that it takes about a few hundred Kelvin before this reaction actually starts to go. But once it goes, it proceeds very fast. Then this will take over. You make OH, and then OH plus H2 makes water. And that is actually the dominant way at high temperatures. And then we have sort of the third route, which is actually on the ice, and that we have basically oxygen landing on an ice and then making water on the surfaces of the grains. And this is actually what we are simulating here in Leiden in our laboratory, where we basically have these very low temperatures, and we are actually making these ices by depositing hydrogen and oxygen. So this is based on our laboratory experiments, both in Leiden, but also in Paris and in Japan. We now think that water is made as follows. So the once a day, a hydrogen atom lands on a grain, that's the white, and then, there it comes, and it will scan the grain, it will find another hydrogen, it will go off as molecular hydrogen. That's how we make H2 in the universe. But we also have these oxygens here on the grains. Yeah, there we have sort of, but there we're making a little bit of O2, and now we're making hydrogen peroxide. Yes, there we go, and now we're making actually two waters. And so we've seen all these intermediate products in the both in the laboratory and also in the observations. And now we speed forward to 10 to the 4 years, and this is now how we build up an icy layer actually on the surface of an interstellar grain. So if you're wondering how the bulk of the water is made in space, then it's actually on the surfaces of these grains prior to the collapse of the cloud out of which our solar system formed. So think about it the next time you drink a little bit of water, as I'm doing here, and you're drinking basically molecules that were more than 4.5 billion years old. That's when these bonds were formed. Since that time, they have sublimated and they have recondensed, but the original bond was formed on the surfaces of the grains in the parent cloud itself. And as one of my colleagues put it, water on Earth is basically older than the sun itself. Good. Let's actually continue still a little bit with chemistry. So let's actually go from cold dark clouds actually to, let's actually now go through these various stages. And let's first go to the cold dark clouds, where we've talked already a little bit about the chemistry. As I said, very cold, a little bit of ionization that's driven by cosmic rays. How often do molecules collide? Well, maybe only once per month. Chemical time scale is long, about 10 to the 4 to 10 to 5 years. Freeze-out time scale can be comparable to this. So actually, in these cold conditions, you actually expect quite a bit of ices. And that's also what you see over here, is that is a nice plot to illustrate it, sort of the chemical or the dynamical time scales compared, for example, also with the free fall time scale of your cloud, or the time scale for ambipolar diffusion. If you're thinking of other ways having magnetic fields for support of your cloud, then your freeze-out time scale, this goes as 1 over square root of n, this goes as 1 over n, so they cross here, and this is where you actually start to freeze out the bulk of your molecules. You see that reflected not just in the ices, we make a lot of ices there, but you also see it reflected in the deuteration. In these cold clouds, that's where we find very high abundances of deuterated molecules, even triply deuterated molecules. So remember, deuterium is made during the Big Bang at a level of about 10 to the -5 with respect to hydrogen. So we would expect ND3 to be at a level of 10 to the -15 with respect to NH3. That's not what is observed. ND3 is at the level of 10 to the -2 with respect to NH3. So this is an enhancement by 13 orders of magnitude. So, and that's really driven by the low temperature chemistry. I won't go through the details, but it's just here a very simple reaction that actually drives the molecules towards the deuterated forms. So remember this as a strong indication of cold chemistry. Of course, we also have the ices that I showed already, the water ice, the methanol ice, the CO2 ice, etc. And we can actually see these also sort of the different types of ices. We can actually see them in our spectra. Now, once the cloud starts to collapse and make a protostar, then we actually start to heat up the cloud. So this, what we looked at before, was just before the source, the protostar, started to heat up the cloud. But when it starts to do so, then all of these ices that we made, this whole beautiful ice layer, will start to sublimate. And it will do that in a sequence according to sublimation temperatures. So for example, carbon monoxide and N2 are very volatile species, whereas ammonia is not so volatile, and water is certainly the least of the volatiles. And so we sort of have a sequence of sublimation temperatures. You can also think of them as snow lines. That's what is it? Kabur behind me has a beautiful snow line there on there, and that's sort of when a molecule goes from the ice to the gas phase. So this is what ALMA now brings. So let's look at, this tiny little protostar there. So previously we were looking always at chemistry in high mass sources like Orion or the galactic center. Now with ALMA, we can actually zoom in into this tiny little protostar here. It's actually a binary protostar that is more like solar mass. And we can start to search for organic molecules, and these deuterated molecules, they are very rich source of deuterated molecules on solar system scales. So actually, if you point ALMA there, we see this whole forest of lines, more than 10,000 lines, approximately one every 3 kilometers per second. So it took quite some time to try and identify them. And we still have quite a number of unidentified lines, actually. Still about 25% of our lines are unidentified. This is some of the molecules that we found now on solar system scales, actually, in these young systems. So again, we go here to tri-carbon molecules. We have here actually the beginnings of CNO bonds, isocyanides that we have here, acetamide. So these are sort of the beginning of peptide bonds, but no amino acids yet. So those have not yet been seen. And again, some of these molecules like formamide, which is quite abundant, if you look at sort of chemistry on Earth for the origin of life on Earth, and then this is always taken to be one of the starting molecules in order to form these more complex amino acids and bases. So how far can the complexity go? Well, we don't know yet. We're searching for it with ALMA. So this goes back to one of your questions. This is how far we've come in the lab. So in the lab, we've already come at very low temperatures without any UV or high temperatures. We've already gone as complex as these sugars like glyceraldehyde, glycerol, etc. So this is a very active field of astrochemistry around the world, making ices, ion bombardments, amino acids, etc. So summary so far, interstellar clouds have a very rich chemistry in spite of the cold and tenuous conditions. And wherever we look with ALMA, almost everywhere, abundant complex organic molecules and water are found throughout the Milky Way and even beyond the Milky Way. So you could say that the building blocks for eukaryotic material are actually quite widespread. All right, this is another good point to maybe pause for a few questions.
Yeah, I'll read another question by Yana.
Yeah.
What's missing for detecting glycine in the interstellar medium?
What is missing for the glycine? Yes. Well, it's partly has to do with that the spectra get so full. So in this frequency range, glycine would have probably several hundred transitions. So those several hundred transitions of glycine are buried somewhere below all these other molecules. So it's sometimes simply difficult to isolate the signals of a low abundance molecule compared with the stronger lines of methanol, ethanol, and some of these other molecules that are on. So we just need to dig deep. We may need to go to different frequency ranges where the spectra are less crowded. And so we've tried to go to lower frequencies to see whether the spectra would get less crowded, but they actually don't. They're just as crowded. We just need to dig deep into the spectrum in order to convincingly find it.
Okay, thank you. Simone Costa also has a question. Go ahead, Simone, you can ask.
Okay. Hello, Dr. Ewine. I'm not from the area, so maybe my question is naive, but there is some consequence for that enhancement of deuterium production that you told about?
Consequence, you mean in terms of?
I don't know, maybe Big Bang nucleosynthesis or...
No. So I think it's important to realize that because these are all minor abundance molecules, that they don't lock up the bulk of the deuterium. They may lock up, maybe 10% or so of the deuterium, but the bulk of the deuterium is still in HD. So in that sense, there are no consequences for the inferring the estimates that are made of the abundance of deuterium in the solar neighborhood. Okay. Yeah, but a good question. Yeah.
Thank you.
Okay, I guess there's no other question now, so you can go ahead.
Right. Okay, so let's go now to a little bit to the physics. So we've talked about ices and how chemical complexity starts to grow in these stages when we go here. But of course, this is where planets are made. This is the protoplanetary disks. This is where we start to form from our submicron sized grains. We start to make our larger grains. So we have grain growth, and we have maybe even planetesimal formation, planetesimal being sort of kilometer size bodies. And I think one of the things that we're realizing now is that much of this starts already in an earlier stage, in the embedded stage of star formation. So a lot of the research is now focused on disks, but there's one major problem, and that's these disks are small. So on the size of this image, this is an artist impression of a disk. Sort of these are tiny, 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 tiny small. And so that is basically, what is it, about a factor of 1,000 times smaller than the cloud. And so this was exactly the reason why ALMA needed to be built, is to be able to zoom in to planet forming zones of disks. So ALMA has been an enormous revolution in this field. This is one survey that I've been involved in, the Lupus ALMA disk survey, which basically said, okay, let's take a cloud that goes right overhead Brazil, goes right overhead ALMA, and that's the Lupus star forming region. That's 140 parsecs, mostly LOMA stars that are formed. And now we're going to just pinpoint ALMA at each of these LOMA stars, young stars, class 2 T-Tauri stars. We're going to point it there for just 1 minute. And that's what we did. And in 1 minute, ALMA detects the bulk of them with very high sensitivity, as you can see. And even with a resolution that is much better than anything that we had pre-ALMA. So even here in our 1 minute survey, we got already 20 AU resolution. So these are the ones that are not resolved. Here you see already some resolved disk and also some of these interesting transitional disks where planets may be forming. But for this part of the story, the important thing is that we have high detection rates and that the material of planet formation is common. Now, then actually, we can look for more. We can stare longer at ALMA with higher spatial resolution, and that's when we can start to see the substructure now in these planet-forming disks. And so here is what you see in this animation, that it's likely that there is, oops, oh, my PowerPoint, sorry, my PowerPoint starts to, what does it do? Okay, where we go back again to that, okay, and then where were we? We were over here, that's, okay, that's, okay, here we were. Okay, so basically what we're seeing here is in this animation that we see there the, oh, what is happening? All right, we better skip that.
Yeah, maybe some problem with the animation.
Yeah, it has this. I've used this so many times, but somehow
Yeah.
it today it refuses to.
Yeah.
Okay, good. We'll skip that. In any case, you got
Okay.
the idea, namely that it's the young planet basically carves a hole into the system, and that is basically what is one interpretation of what is causing these gaps there. In fact, we see them in many disks. This is an example of a source. This was ALMA cycle 0 data. And then this is sort of what we got with higher spatial resolution in cycle 5 data. Now in band 4 at 1.9 millimeter, you see that sometimes these asymmetric structures then start to change into a very symmetric dust ring, and then here sort of a dust trap at the bottom. And this has really led to a new era of observational planet formation. Starting with one of our early results of this dust trap that we have over here, that was even before the famous H-tau image, then another image, more images, rings, gaps, cavities, spiral arms, just everything that is coming there. And culminating now in this impressive high resolution sample of the 20 brightest disks that was taken by Andrews et al., the D-sharp sample, where almost every disk shows indeed rings, gaps, spiral arms, etc. But you have to realize this is a biased sample. These are the 20 brightest disks. And the question is really, how common are these structures? What do they tell us? But also, how do they fit into the general disk population? And it's not yet clear that the other part of the population that also has as much structure as this subsample has. So again, summary here is that nearly all the young stars are surrounded by disks. The sizes of these disks are comparable to our own solar system. And the masses of young disks are actually enough to form planets in most of the case. The structures in these disks then likely point to planet formation in action, although the detailed interpretation of these structures is still very much under debate. And in fact, let me just go to one explanation for these disk structures, and that's the snow lines. So here again, you have the beautiful volcanoes that you have here in Chile and Bolivia. And here you see again a snow line, water going from the gas to the ice. And that's also what you have in your disk. Close to the star, it is warm. Water is in the gas phase, but then at some stage it will start to freeze out. That's your water snow line. Then you get your CO2 snow line, and then you get your CO snow line. These snow lines are important because they enhance the mass of the solids, which is important for planet formation. And it also changes the carbon over oxygen ratio of the gas and the ice. And this is from the nice work by Obergedal, where they showed that ices are always oxygen rich. We saw that when we looked at these spectra of interstellar ices. A lot of water and a lot of CO2 is there. And that means if most of the oxygen is locked up in the ices, that means then that the gas is going to be carbon rich. So if you're thinking of an exoplanet that is being built somewhere over here, the outer part, where almost all of it is frozen out, then your atmosphere, if it accretes mostly from the gas, will be carbon rich. On the other hand, if it's more over here, and if it accretes primarily from the ices, gets its heavy elements from the ices, then it will be actually an oxygen-rich atmosphere. So very important for tracing sort of the chemical composition. And again, comparing that even with our own solar system, then there's always been this interesting sort of point made that Jupiter is right behind where we thought that the water snow line was in our young solar system. That this was where water was frozen out, it piled up here, and that was why it was easier to make sort of the critical mass that you need to build a giant planet core to make it there. And then you have the giant planets there. Whether that is also happening in the other planetary system is, I think, still something to be determined. Okay, but the point is with ALMA, we can start to trace these snow lines. This is one example, early example of tracing the carbon monoxide snow line in a young disk through a tracer, actually, in this case, protonated nitrogen. And this whole point of linking sort of gas, dust, and ice with what we get ultimately in exoplanetary atmosphere is a very rich field at the moment. We have here the example, what I just described, the icy grains and the rocky grains, but these grains grow, they grow to collide, collect, and make planetesimals. The planetesimals can actually start to drift, this sort of the millimeter size, the pebbles can start to drift inward. And they can take some of their ice material with them as they cross here some of these snow lines. So there's a lot of interesting dynamics also going on in the disks that ultimately can either enhance or can also deplete sort of the planet forming regions in oxygen of nitrogen. So these dust traps that we see, these structures that we see in ALMA, in the rings, they can trap heavy elements and lock them up in the outer depth so that the inner disk has very low abundances. But it can also be the other way around. If there are no dust traps, then they can move inwards and they can actually enhance the inner disk. So very interesting interplay between sort of these icy grains, pebbles, and planet formation. Okay, questions here, because then I still want to say a few words about comets.
I have a question. When you show this this place where it's preferred to form giant planets like Jupiter and Saturn, but what happens in systems when you have giant planets closer to the stars?
Yeah, very good question. That's always were they formed there or not? I think every planet formation theory concludes that it's very difficult to make the hot Jupiters, as we call them, to make the hot Jupiters very close to the parent star. More likely, they were formed somewhere between around 5 astronomical units, typically. A few astronomical units, maybe out to 10 astronomical units. That's maybe where the bulk of them formed. We don't know yet. We don't see that many really giant planets at larger distances through direct imaging, although we still lack sensitivity there. But basically, if they're formed over here, then once the gas has gone, then they can have, of course, interactions between them, dynamical interactions with maybe a third body. And then you can get migration in the disk. You can have, of course, migration in the disk already when the gas is still present. When the gas has gone, then you can have an interaction with a third body that sort of get you into a quasi mechanism that can bring the giant planets into the inner part.
Okay, thank you. I'll read another question from the chat by Maria Jaqueline Vasconcelos. There were an early claim that MHD instabilities could cause the asymmetry seen in the images of disks. Is this still being considered as a viable explanation from the observational point of view, I mean?
Well, the asymmetries that we see, the azimuthal asymmetries that we see in the disk, the one case that I showed that is the most prominent, and that you see also here, for example, these azimuthal asymmetries is, and then this is the most extreme example. We think that they're actually due to the Rossby wave instability, which is a sort of a well-known phenomena where you need to have, need to satisfy certain conditions before it can appear, also in terms of density. But we think that this is still one of the most likely explanations, that you get sort of these azimuthal asymmetries.
Okay, and Daniela also has a question.
One question is regarding the snow lines. The snow lines during the formation, the planetary formation, the star also is changing, is forming. So the snow line will also move.
Exactly. Yeah. The snow lines move. The snow lines move inward.
Inwards, yeah. So you have a movement also to consider.
Yeah. You have to take that all into account when you. I think this is actually shown here also. That here's the snow line. You see the snow line move inwards. So yeah, you need to take that into account. That's absolutely, yeah. And that's the interesting part, because we think now, and there are various reasons for it, that most of the planet formation took place already early on in the embedded phase of star formation, when the snow lines were further out. So there's probably more in this stage than in this stage. So that is an interesting point to consider. Yeah.
Okay, I see no other questions now.
Okay, let me then just continue on the final part, which is basically this, well, actually the growth from grains to planetesimals to planetary embryos and to comets. And that is basically this interesting part in between. So basically, this is the, oops, yeah, sorry. I'll let it actually, sorry, I forgot to turn off the sound, but it took away. This shows very nicely what I think is happening actually. Here you have all these small bodies that actually colliding with each other. Some of them may also lead to destructive collisions. This is basically how you make sort of these larger bodies that form sort of the basis there. And this, the planetesimals, as I said, are an important intermediate step, because this is where gravity starts to take over. This is when gravity between the individual bodies can start to take over and control the dynamics. And that's just the size of comets. So comets are really, the planetesimals, comets are really the building blocks of planets. And now, thanks to Rosetta, we can actually measure the comet molecules in situ, whereas in our young disks that I showed earlier, this is where we observed the just sublimated ices. And so this is then the question, are these ices actually preserved from cloud to comet? So Rosetta had a very good nose, a double focusing mass spectrometer. This was built by the University of Bern, PI Katrien Altweg. And it sniffed at sort of 10 kilometers distance. It was not on the lander, it was basically on the orbiter around the comet. It traveled with the comet for 2 years, and it sniffed a lot of the gases that you see over here. And many of these gases were actually the same gases as what we see in our protostellar envelopes, in the ones that I showed you in our little protostar. And so here you see sort of the whole zoo of molecules that you see here. I like this sort of comparison with the zoo because we clearly have some very smelly molecules like hydrogen sulfide. These are the skunks. We have some noble gases that we have here, and we have some. Oh, here we have the noble gases, actually, yes. And here we have the nitrogen, the oxygen, the hydrogen peroxide, some manure that we have here, ammonia, methylamine, here the monkeys with the methanol, the ethanol, etc., the formic acids, some of the giraffes with the methane, propane. So a whole variety of molecules, and many of them are very similar to what we see in our interstellar clouds. So that is actually sort of where this whole field is going, is sort of to link exoplanets, solar system building blocks, comets, and disk compositions. You see here all these planets coming out of the disk, and that's where they get their building blocks. And this is how we determine the chemical composition. And it's of course wonderful that we have future instrumentation coming up, JWST, I mentioned already. Launch hopefully late 2021. I'm part of the team that co-built the MIRI instrument. So we're looking very much forward to mid-infrared observations with JWST. And then the ELT from the European Southern Observatory, which will have the MATIS instrument, again mid-infrared instrument. And that will hopefully be see first light around 2027. So I hope that to have given you a little bit of a flavor of this field. On one hand, chemistry, lots of chemical molecules, both simple like water, but also more complex organic molecules present throughout space, associated with forming stars. We've talked a little bit about the exciting area of planet formation and protoplanetary disks, where there are lots of observational advances at the moment, thanks to ALMA. And we're only starting to sort of get an impression there, sort of what kind of planets are formed. I mean, how do we form the giant planets, but also, you know, what are then the conditions that lead to these super Earths and mini Neptunes? Why are we forming a lot of those? And the new solar systems then are being unraveled with the new instrumentation and technology. So that's great. And hopefully it gives us a little bit of impression as to how we were formed some 4.5 billion years ago. Thank you very much.
Thank you. Thank you very much. I mean, it was amazing. It's an amazing universe of molecules. It's really great. Thank you very much. I'll read another question by Jana. So coming from an extragalactic background, I have noted that morphological similarity of a protoplanetary disk and a accretion disk of an AGN. Can you comment on it? Are there other common features?
Yeah, no, that's a very good point. There are a lot of similarities there. Of course, the size is a little bit smaller, the mass is a little bit smaller, but in terms of dusty disks, their structure, even some of their chemistry, and the fact that you can crystallize silicates in there, and those are all similarities. Of course, the jets that we also have. AGN, of course, different energies, relativistic regime. We are not in the relativistic regime, so that is different. And there may be other, you know, differences in structures, but I would say also both in observational and modeling perspective, there are also quite a bit of similarities there.
Okay, great. Marcelo.
Yes, thank you very much for the talk. It was really nice. I like it very much. I have actually two questions. One is about one of your last slides, where you show the growth from the kilometer-sized bodies to planets. Okay, but my question is concerning the growth from grains to centimeter-sized bodies or particles, because sometimes if you have very energetic collisions, the grains can be destroyed. So how can this work?
Yeah, no, that's a good point. What you saw in that little movie was actually that they were not mostly constructive collisions, not destructive collisions. But indeed, if the velocities are too high, then they will just simply destroy, and then you have to start from scratch again. So you have to make sure that the velocities are not too high, which is exactly what is happening in these dust traps, because in dust traps, basically the small difference between the velocities of the gas and the dust are minimized, because you are basically at a pressure bump. So that helps, and in these dust traps, that's where you can grow. You have sort of a safe haven to grow. So that is good. Then I think the critical point is really these sort of collisions can get you to sort of pebble size. Pebble meaning sort of literally like a pebble, a big pebble on the beach. But then getting to planetesimal size, that's not that easy, and that's where you need to invoke some of these what is called streaming instabilities in disks, where you collect, where you have low gas to dust ratios, and you can collect a lot of dust together that can basically collapse into a kilometer-sized body. But that's sort of the least understood step, I would say, the going sort of from pebble size to kilometer size. Yeah.
Okay, thank you. And my other question is a little bit linked to the first question of Jana. So, for example, concerning astrobiology, which are, in your opinion, the next steps, the future from astrochemistry for example, for the identification of biosignatures in the atmosphere of exoplanets, especially rock exoplanets?
Yeah, no, that's a whole open field. I mean, that's. I think first we need to search there for the simple, the simple molecules like water, ozone, maybe some nitrogen oxide, of course, methane, etc. We need to look for combinations of biomarkers in order to see whether there could be possible life on those planets. More complexity will be difficult to do with remote sensing. So I think that is why some of these sample return missions, like we now have from some of the asteroids, are going to be important to sort of see the complexity that one has there in terms of organics. If I look at sort of what Rosetta has shown us about a primitive body like a comet, it's amazing the complexity that you have there to the chemistry. Yeah, but I think there you need to really start doing the either land on the body and do sort of in situ measurements, or bring them back to Earth. And that's yeah.
Okay, thank you so much again for the nice talk, and also for accepting our invitation. Thank you.
My pleasure.
Okay, Jorge also has a question. Go ahead, please.
Thank you, Simone. Thank you, Ewine. This is a fantastic lecture. My question is, can all the building blocks of life be formed in space, in the interstellar medium or the interplanetary medium, or do we have to form some of them on planetary surfaces?
Well, yeah, so certainly if you think of origin of life on other planets, you don't have to bring really complex molecules from outer space on that planet. As long as you have some things like basic ingredients like water, some nitrogen compound, HCN, or any of the nitrogen-bearing molecules, cyanides will do there, of which we know are quite abundant in the interstellar ices. And then maybe some formaldehyde. You can already kickstart then the chemistry to make on a young Earth where you also have liquid water. Of course, in interstellar space, we only have ice and gas. We don't have the liquid phase. But on a young planet, you will have a liquid phase, and that's where you can build a lot of chemical complexity. So in the end, you may have to bring in only some of the basic building blocks to a young planet in order to kickstart the prebiotic material there.
Right. So, but if you need, if you can form them on the surface of planets, can now the amino acids be formed in space?
They can be formed in space. I mean, there's no. In fact, we've just published a paper in Nature Astronomy earlier this week that we demonstrated in the laboratory. We can make it without needing any UV or energetic processing in the laboratory under interstellar conditions. So, in fact, personally, I have no doubt it's been detected also in comets. That some amino acids will be present there. The question is whether you would, and that you can also bring them to young planets and maybe help kickstart life. The question is whether they are essential to do that, or whether you can also, bring basically the chemistry on the young Earth to do that.
That's great. Felipe also has a question.
Hello, thank you for the amazing talk. First of all, it was really a great review. My question follows that from Marcellus, from the pebbles formation to the planets, and it's maybe a simple question, but I want to know if the ices can have an important role on building the kilometer-sized blocks. I mean, if can we think the formation of rocky planets without a lot of ices in the inner region, or do we need to form them on the outer region, or the formation is more effective?
Yeah, that's a good point. So for a long time, there are lots of papers that say that if you have water ice coated grains, that they will stick more easily together, that they become more sticky. That's a little bit being debated at the moment by laboratory experiments. There are some fantastic experiments being done, for example, by Jürgen Bloom's group, where they really have these collision experiments in the lab, also with ice-coated grains, even under microgravity conditions. They go through these parabolic flights and get very sick, but they do their experiments also. And I must say that it's being disputed at the moment. And then the question is, maybe water ice is not so sticky, but maybe carbon monoxide ice could be more sticky. So there's a little bit of debate at the moment in the literature as to whether ice-coated grains stick more easily or not. Certainly they increase the mass, and already increasing the mass, that also helps in bringing them together.
Okay, thank you very much.
Okay, thank you. So we have another question from YouTube. Lucas Correa is asking, what do you think will be the impact of the ELT on this field of research?
Yeah, in various ways. I mean, of course, ELT will have unprecedented spatial resolution, 39 meter. So JWST will be great in having sensitivity. So it will be be able to do transit spectroscopy of atmospheres of super Earths, of course, of giant planets, but also of mini Neptunes and super Earths. So JWST have great sensitivity, unhindered by the atmosphere. That's fantastic, but ELT will have sort of the high spatial resolution. Now you can get down to, say, a few AU in terms of imaging. What the disk images are telling us is that there's lots of structure and that there are likely planets forming, but we haven't seen those planets yet with direct imaging. We simply haven't had the sensitivity yet to do so. Even with VLT, etc. Most of the limits are still at sort of the several Jupiter mass. Whereas it looks more like it is of the order of, say, they might be Jupiter mass planets or Saturn mass planets that are forming at the larger distances. And that is where the ELT will come in and and observe those. Yeah, and of course, in mature exoplanets, then and that's very important also, spatially resolved spectroscopy. So the moment you can separate the light from the star from the light of the planet, you can take a much more accurate spectrum. We see that already with VLTI gravity, the spectrum of Beta Pictoris. Once you have spatially resolved, you're in a totally different ballgame in terms of modeling your atmospheres. much more accurate. So much higher signal to noise. So that is also what ELT will do, spatially resolved spectroscopy.
Yeah, that's great. It's exciting. Future with lots of new data coming. Okay, any other question? I think there is no other question. So I want to thank you very much, Ewine, for this very nice talk. It was a great review. I hope we have the chance to have you here with us in the next time when all this is over and you can come back to normal life or some kind of normal life. So
yeah, good. Thank you very much for listening. Maybe if I can have sort of a 1 minute putting on my hat as president of the IAU.
Sure.
And still telling all of you the importance also of your union, your International Astronomical Union, and drawing attention to some of the activities that we're doing, activities in education, of course, in research and education, in outreach, in development. If you want to read more about it, please go to our website and also to the website that we had for recent celebrations of 100 years under one sky, where we look back at sort of 100 years of astronomical discoveries, but also looking forward to what our field will bring. And one of our activities was actually Name ExoWorld, where every country got to got one star and one planet to name. And this is actually through an open competition with everybody, the whole country involved. And this is actually your choices here of the name of the star and the exoplanets. And I understand that these are indigenous people here from your country. So it's great to see them being recognized in this way. So I actually would like to leave you with that and just remind you all and send you home sort of with this idea that we're all sort of these world citizens under our beautiful sky. Thank you very much.
Thank you.
Thank you so much, Ewine. I hope to see you soon.
Okay. All right. I wish you all the best, and I hope you're doing well, and that you stay healthy and stay safe and stay healthy. That's
you too. You too.
Good talk.